Hello, my name is Richard Everitt. I'm at the University of Warwick. This is joint work with Evis Kramer at Reading and Tom Thorne at the University of Surrey, and this is called Rare Event ABC-SMC squared. I'd also like to acknowledge Dennis Prangle for useful discussions, and also our funders, NERC, who are part of UKRI. So this is going to be a very short talk about a new ABC method. We're going to set this up by talking about how ABC, the approximate likelihood that's used in ABC, and then describe very briefly a previous approach that we're building on here called a rare event approach to high dimensional ABC, and then we'll give details of the new approach. But of course, there's going to be very little detail in this talk, with it being very short. If you want more detail, then there's a draft paper online and also another longer talk find easily on Google, and on that page they link to the draft paper that isn't yet on archive. Okay, so let's start briefly by mentioning ABC. So ABC is an approach we use when we can't evaluate the likelihood f at theta. So why is the data, theta is the parameter that we want to estimate, and we can't evaluate this pointwise at theta. But we can simulate from the model. So the idea of ABC is to assess whether theta is plausible by simulating some sort of fake data x from the model and seeing if the statistics of x are close to the statistics of y. That's the observed data. And essentially, if the statistics are close, then we judge theta to be good. We give it a high likelihood, and this is an approximate likelihood that, as we'll see in a second, we're estimating using these simulations. So some challenges in ABC. Firstly, exploring the parameter space. There's a number of methods for doing that, and we'll come back to that in a few minutes. But the thing I wanted to mention about this on this slide was about the approximations that is introduced. So essentially, the simulations that we're using give us this. Essentially, we're estimating the likelihood with this thing L hat at the bottom, where we evaluate this pi epsilon here, evaluates the sort of plausibility of these simulated xn's. We're going to simulate more than one of them. We're going to simulate nx of them compared to the observed data. And this expression here is a Monte Carlo estimator of this expression above, which we're going to call L, which is sort of the true ABC likelihood. That's really what we're aiming at when we use ABC, and we get at that by using a Monte Carlo estimator. Okay, so this is a challenge because firstly, this approximation we use here isn't the true likelihood. It introduces some bias, although it's sort of the true ABC likelihood. There's an approximation going on here, and we also have extra variance by the fact we're using x variables here that are simulated, and we're using Monte Carlo to estimate this. So, and the variance here will mean that our whichever Monte Carlo method we use to explore theta space will be less efficient. If there's more variance, it will not be very efficient. And in lots of cases in ABC, we see that to get a good when this approximation error is small, the variance that we get from this likelihood is very large, and so these approaches are very inefficient. So an approach to helping out with this is to look at unpacking this sort of black box simulator, being the model. So what we do is we, instead of just saying we simulate from F, we try and break down this simulation into different bits. So we say, well, this consists of simulating some random variables U, and then doing a deterministic transformation on them, which is called H. So I think pretty much most simulators can be viewed in this way. And the advantage of doing this is that the intractable F term here has disappeared from the um, from the expression here. And this is something that's been used in a number of different approaches already, including an approach to exploring this theta and U space efficiently using HMC. So the idea here is that we're trying to exploit is that what we're going to try and do, rather than sort of blindly simulating from this F, we're going to try and tailor these U variables so that they will produce good simulations somehow. That's very roughly speaking the idea here. And because this expression doesn't involve evaluating F, we have at least some freedom to do this. So this approach has been exploited before in this Prangal et al., which is the rare event ABC-SMC paper that I mentioned at the start. The insight here really is to see that the estimator we're using that I introduced a couple of slides ago, this one here, can be seen as an importance sampling estimator of this thing here. Essentially, with this thing here being the normalizing constant, and this being the importance sampling estimator of the normalizing constant, where this is normalizing this integrand here. And we know that importance sampling doesn't have nice properties as the dimension of the data grows, the dimension of x here, or the dimension of u. So a nicer way of doing it that scales better is sequential Monte Carlo, as long as it's set up well. And rather than having a need to have an exponential number of points in the dimension to stabilize the variance here, we can get away with a quadratic cost. And essentially the idea in this Prangal et al. Is rather than using the importance sampler, just to use an SMC instead. And this isn't the same as ABC-SMC, which is a more well-known technique. ABC-SMC is a technique that's used on the joint space theta and u, or theta and x. And this rare event approach is an approach that explores the u variables given theta. Now, I have got a couple of slides about this approach. I'm just going to show them very briefly, so if you want to pause the video and have a look, you can, but I'm not going to talk about them. This is just showing the sequence of targets that's used in the rare event method SMC for estimating the likelihood. And this is a little bit more detail. And here's a little picture of what happens to these u variables as we use this method. But I'm going to talk about them more when we talk about our new approach. So really I'm just going to summarize the benefits of doing this rare event ABC-MCMC. Well, it's going to beat standard ABC-MCMC as the dimension of the data grows, as long as you can set up this SMC algorithm well. Essentially, because the variance of the likelihood estimators are going to be is going to be better. But we have all the usual issues still, or many of the usual issues of standard ABC-MCMC, in that we have to tune them well to make them work, and we have to sort of fix an epsilon value that is reasonable. Epsilon's the sort of tolerance we allow between the simulations and the observed data. ABC-SMC is used a lot in SMC because it has some nice properties in terms of being able to adapt the algorithm automatically. And so what we're going to do is use this rare event SMC approach for estimating the likelihood within an SMC approach for exploring the theta space. So the sort of key thing that's going on here, I should say this is very similar to the SMC squared approach used in state space models from a few years ago by Nicolas Chopin and co-authors. Essentially, if we're using this sort of ABC setup, and we set up an SMC algorithm, the sort of idealized weight that we would be looking for in doing the incremental updates as we move from target distribution to target looks like this. So this is sort of an idealized algorithm if we could analytically get this likelihood, which we can't. So what usually happens in ABC-SMC is that instead the numerator and the denominator here are replaced by these estimates here, and that's the standard ABC-SMC algorithm of Delmorel et al. From 2012. What we're going to do in this method instead is we're going to use a step of an SMC sampler on the space of U variables to estimate this ratio every step to get the incremental weight. So we're going to end up with a sort of random weight SMC algorithm that uses this ratio estimator at every step. So again, the details of this are in the draft paper, but here I wanted to show a picture to show what's going on that's different from ABC-SMC. So what we've got here is we've got some particles in theta space. So this box here represents a particle in theta space, as does this one. So we've just got two particles here, and this is the first step. And for every theta, we draw some U variables. So these little black dots are the U variables. And the crucial thing here in ABC-SMC is that when these U variables are generated at this first step for this theta, these live together with this theta as long as this theta is alive. Okay, so this one has one set of black points, this one has another set of black points. And what happens in ABC-SMC is that weight update is based on these U variables in the way that I had a slide or two ago. And then when we iterate the SMC algorithm on theta space, well, at the next step we will lower the tolerance. Okay, so we get a smaller circle here. That's what this circle's meant to represent here, sorry. To begin with, these U variables were drawn within this box, and the circle is the representing within the circle is within epsilon 1 of the data. Okay, so at this second step, the smaller circle here is being within epsilon 2 of the data, and we see that since these U variables, these black dots, live with the particle, essentially we just get fewer of them being in the red circle here. And then what happens is that on theta space we do MCMC moves. So we propose new thetas, and with each new theta we propose, theta star here, we generate some new black dots, some new U variables that go along with this theta star. And if this turns out to have a better likelihood, then there's a good chance that we'll replace one of these existing particles with this new thing here. So in fact, that's what we're seeing happen at the next step. Instead of taking forward this one's being replaced by this here, which again, if you can see, has the same black dots as this proposed theta here. And then again we shrink epsilon and we calculate our weight update again. Now the problem here is that the you can see that we're getting this red circle is getting small enough that we have very few black dots falling in the circle, which is going to it's going to give us a high variance likelihood estimator. So in the new approach, the Everitt ABC-SMC squared, essentially what's happening is that we have the same kind of setup in theta space, but the U variables work slightly differently. So again, at the start of the algorithm, the U variable is drawn for this theta variable, and then we draw this. We have the first weight update, and some of these things will fall outside the epsilon tolerance. What we do instead, rather than sticking with these black dots all the way through for this theta, is we do an MCMC move at a resampling step, such that we sort of juggle these thetas into a better position. And now all these these U variables into a better position. So all these U variables are now inside this circle, which is going to be in a better position for estimating the likelihood at the next step, or the likelihood ratio at the next step. So at the next step, what happens now, look, is that we take this theta and these black dots from here, and these things here are used again in the weight update, Again, now we're looking at the ratio in the weight update, so we can see the number in here compared to the number in here. That's essentially what the ratio likelihood will look. The ratio weight update will look like. And then we again do an MCM a resample, then an MCMC on these U variables, and we get them again nicely inside this circle here, which is going to be a much better position for when we are at the next step. Okay, so then the thing that's also slightly different is that now our MCMC on theta is going to be a bit more complicated because we have to go right from the start. So we have to, again, for every theta we generate, we have to generate some initial U variables, which we're going to walk through this process until we get to here. And this will give us a likelihood estimate. And then we see whether this one replaces one of these theta variables or not. And in this case, it did. And what happens then is that if we just look at this one replacing this one, we have these black dots that are in this picture go over to being in this picture to estimate the weight update again. But we can see we're getting more of these black points in this smaller circle, so we're going to have a lower variance likelihood estimator, or ratio estimator in this case. Okay, so I haven't got any results in the talk. I just wanted to introduce the idea. So we've got an SMC squared style method for doing ABC-SMC. And the advantage here is that it should allow us to go to higher dimensional data because we're no longer using the sort of standard importance sampling estimator of the likelihood in the numerator and the denominator. Instead, we're using an SMC style approach that estimates the likelihood, the weight updates via SMC moves. And we see that this produces better empirical results compared to the standard ABC-SMC. Okay, thank you very much. I'm very happy to answer questions by email.